Okay, I'm going to go ahead and get started. So, what have we been learning about? Oh, that was yesterday, and that was not in class.
AC systems.
AC systems. Okay. And what is an AC system? And all alternating current stands for is the forcing function, which is the power supply, is a sine wave or a cosine wave. Okay. So we've been learning about this. We talked about phasors. We talked about how these types of systems, how to really calculate addition of them. And all of that is building to this point. Okay? As of right now, we know, let's talk about our component equations for a little bit. Okay? Here, with our component equations, what we have is you've got three of them because we have three components we've been focusing on. For resistors, it's VR equals IR times R. For a capacitor, it's VC is equal to, IC is equal to C dVC dt. And for an inductor, VL is equal to L DIL dt. Okay? So this is nothing new. If we were to take this and apply what we know about current and voltage and sine waves all together, we get some very interesting results. Okay? So here, if you take your current, I think the example that the book gives is, if you just have a standard if I is equal to, just like A cosine omega t, then what that means is that for your resistor, VR is going to be equal to R times A cosine omega t. I mean, shocking, right? So this equation stays true. There's no way of simplifying it. It's already pretty simple application there. We know what voltage and current is. You want to find what the current value is, you divide by R. Very simple. Okay. But there is a little bit of a different behavior for both the inductor and the capacitor. So here, if we say that IL is equal to A cosine omega t, then that means that VL is equal to L times the derivative of IL, which is equal to L times the derivative of A cosine omega t, which means that VL is equal to negative omega A sine omega t. Okay? Another way of writing that is that, because we're trying to get things in terms of cosine, and here I have to look at my formula because I do not ever remember these. VL is equal to negative omega A times cosine omega t minus 90 degrees. Okay, so what we can say for that is that here, this is our original voltage equation. For an inductor, VL is equal to negative omega times negative J, which just ends up being negative omega times negative I times A cosine omega t. This is how we get rid of that negative 90 degrees. So we just put it in parametric form, which means our VL is equal to I in the negative sense. Yeah, it just becomes, oh, and I forgot an L. Omega L times our original IL. Okay. And it turns out you can do this for capacitance too. The book derives these equations. And yeah, so this brings up an interesting opportunity, okay, to what we will now refer to as the complex impedance. Okay, and the idea of a complex impedance is that if we take these in phasor form, the derivatives and the integrals of these functions become identical functions to our original functions. We can just put them in phasor form again. The derivatives and the integrals of a phasor is another phasor. And for that reason, we can write every one of our component equations as V component, I don't know, we can write it as like VL equals ZL IL, VC equals ZC IC, and VR is equal to ZR IR, where all these Z's are complex impedances that allow us to combine these two. If we write them in this form, this is our new component equations. This one's a lot easier to remember because they're all Ohm's law looking things. So we like easy, but we do have to define what ZL, ZR, and ZC are. So going off of this idea, ZL here has to be equal to omega L times I. The book uses J. That is a pretty common way. Oh, excuse me. J and I are identical. It's just complex number form. A lot of electrical engineering uses J instead of I, but I like the letter I because it makes sense to me. So ZL is equal to omega Li, which is equal to omega L at an angle of what, 90 degrees? Yeah. And that's just because you can take a negative of a cosine and it equals the positive of a cosine. On the other side, ZC is equal to 1 over omega c, negative 1 over omega c times I, which is equal to 1 over omega c at an angle of negative 90 degrees. Okay, and the hardest one to remember of all, make sure that this is true before I tell it to you. Do not have these equations memorized. Is that ZR is equal to R. That one's pretty easy. And all that is it's just because they have the same time form here. If you plug this in, you just get the same function out multiplied by R. There's no derivative, no integral involved. They're just buddies. Okay, and I will go ahead and say that this is also equal to R at an angle of 0 degrees, just because that'll help you out in a little bit. So there's our component equations. These are the new ones. These are only valid for AC systems. But because AC systems have this unique behavior, we can use these component equations that are complex in nature. We can use them to solve problems, and it should make our lives easier. Okay? So, how does this make our lives easier? Well, I'm going to throw a circuit up on the board that some of you may love, some of you may hate, none of you love. I'm going to resurrect an old devil, hand it to you, and torture you with it. It is the RLC circuit. Welcome home. Okay, if we want to know Vs is equal to, I don't know, let's do standard outlet. 120 times cosine of omega t. Okay? And we'll say R is equal to 1,000 ohms. We'll say C is equal to 10 microfarads. And we'll say L is equal to, you know what, I like tens. 10 henries. Okay, and we know that the frequency of this system is equal to 60 hertz. Okay, and what I want to know is how much power is being provided to this circuit by the power supply. How do we determine power in AC systems? It's not an average. If we just take the average, it's 0. P is equal to IV, yes, but there is something special we have to do to this. Because if we just take the average value of I and V, they're both 0. So we have to do something special to this.
What we did last class.
What we did last class. Nice. Way to not look in your notes at all and just tell me to just remember what I'm telling you. But you are right. Dang it. Here, we're going to need to find PRMS. Okay? PRMS is equal to I RMS times V RMS. VRMS is just what? V over the square root of 2, I think. And I think that might be the same for IRMS. I don't know, I'll look at the formulas when we get there. But that is what we're looking for here. We want to know PRMS for VS. Okay? All right. Well, this is where we start our 7-part solution problem, right? And I cover 3 boards? Yep. No. See, the nice thing about impedances, and what we talked about in the last class, is that you can add phasors. And we know how to do that now, because that's what we covered last class. All 3 of these are phasors. And you can add them. And that's not too terribly hard. Although it's weird, because phasor math is weird. So, let's do it. So what we have here in this system remains true. KVL, KCL still have to exist. This marker is dying. I'm even close to the trash can. Dang it. Okay. What is KVL for this system? How many loops do we have? So with our 1 loop, what equation do we get? It's a plus. I heard plus from you. Okay, and then if we plug in our KCL equations, all we find is that IS is equal to IR is equal to IC is equal to IL. Because we only have 1 loop, all of the currents have to be the same. Everything in series, current stays the same. Okay, so this is fun. Let's derive our constitutive equation. Here, we're going to go ahead and solve for the current through the system. And the way that we're going to do it is by saying, you know what? Let's say VR plus VC, let's say ZR plus ZC plus ZL is equal to Z equivalent. And can we find an impedance equivalent to this by where VS is equal to Z equivalent times IS? The answer to that is yes. We can add phasors. We've done that before. Now, all of these components are in series, and which is why if you add them together, it's like this. If they're in parallel, it uses the parallel resistance formula. But you get exactly this. Here, Vs is equal to ZR IR plus ZC IC plus ZL IL, right? Because that's our new equations, new component equations, which are kept on the board for this exact reason. Okay, we know from KCL that IR equals IC equals IL, which means all of them equal IS. So this becomes Vs is equal to ZRIS plus ZCIS plus ZLIS. We can simplify that to Vs is equal to ZR plus ZC plus ZL times IS. Or this is our Z equivalent. It's not too crazy yet, right? Not yet. Awesome. So how do we actually add them? Well, I'm going to keep these up on the board because I need them for reference. I don't have them memorized. But the idea here is we have the J formulas, well, the I formulas for all of these already. They're already broken out. When we added phasors, we had to break them out into something plus something I. That's what we had to do. This is already broken out into that form. So we have here R plus omega L I plus, oh, that's a minus. This marker is dying. And I still can't hit the trash can. We'll murder all of these markers by the time class is over. 1 over, oh yeah. That's nice. So here, our Z equivalent is equal to R plus omega Li minus omega C times I. 1 over omega C times I. Okay? All we have to do is figure out those numbers. Here, this is real, this is imaginary, and this is imaginary. We add those together, we will get a phasor. We get a phasor, we're done. We've calculated now what the relationship is between Vs and Is. Once we have that, then it's just a matter of multiplying. We're that close. We didn't have to do that 7-step process. Which is why a lot of people love AC systems, and they shouldn't, but they do. What's omega? Do we know omega? Did I give you omega? I gave you your frequency. Good work looking up old formulas. Thank you. So I didn't give you omega, but I gave you the frequency. And you have to calculate omega using the frequency. So omega is equal to 2 pi times f, as Dylan pointed out, which is equal to 2 pi times 60. So our omega, pull up my handy dandy calculator. is 376. Oh no, that's 377.0. And that is units of radians per second. It's an angular frequency. Okay, so now we have that. We know what L is. We know what C is. Let's go ahead and find out what ZEQ is. So ZEQ is equal to our R value is 1,000 plus 377 times 10 I minus 1 over 377 times 10 microfarads, so which is 10 times 10 to the negative 6th I. So this becomes ZEQ is equal to 1,000 plus 3770 I minus, well, this is going to be a big number. Or not. 265 point, no, we don't need a point. I, truncating there. So if we combine our two imaginaries, we get ZEQ is equal to 1,000 plus 3505 I. Here's our real, here's our imaginary. If we go ahead and put this as a phasor, that means that Z equivalent, I'll just do some quick head maths. Dun, da, 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 dun. $36.44 at an angle of 74 degrees. So 36.44 at an angle of 74 degrees, and that's our complex impedance. You are in the way. So, our final equation here is P RMS is equal to V RMS I RMS. Well, guess what? We have a relationship between V and I. It just uses our complex impedance. So that means PRMS is equal to V squared RMS divided by Z equivalent. All I did here was I just plugged in V over R in for I. That's it. So, and you get that equation. So it's PRMS equals VRMS squared divided by Z equivalent. Nice. Or we could go the other way and try to figure out what I RMS is or something. Okay. So what we have for, what is VRMS? VRMS is, it is V over the square root of 2. I'm pretty sure of that anyways. I'm going to make sure before I agree with you. Thank you, book. I am using you as a crutch. Yes, it is. It's V. Yeah, it's just V over the square root of 2. Okay. Oh, shoot. If we do it this way, we'll actually get... I have to keep this as a... Dang it. We have to keep this as VRMS IRMS. Because this becomes VS over the square root of 2 times IRMS, which we didn't calculate. I should have calculated that. We need to find out what the equation is for I so that we can figure out what IRMS is. Which is not hard, by the way. So IS is equal to VS divided by ZEQ. Okay, so this is equal to VS is 120 cosine omega t. Oh, nope, sorry, I'm gonna put that in phasor form. 120 angle at 0, because there's no phase angle shift on our VS. It's already in cosine form, so we don't have to do the negative 90 thing. There's no phi. So 120 divided by 3644 angle of 74 degrees. How do you do this? Well, using my crutch over here, just because I want to make sure before I tell it to you. All you do is you divide these two numbers and you subtract these two numbers. Hard maths. That was the answer everybody was hoping for. Okay, so 120 divided by 3644 is equal to, IS is equal to 0.03293 at an angle of negative 74 degrees. Okay, now we take this, and IS is equal to what? I over the square root of 2, IS RMS. So IS RMS is equal to IS, the maximum, divided by square root of 2. So if we divide this by the square root of 2, this becomes 0.02329. Nice. Which means that PRMS is equal to VS over the square root of 2 times 0.02329 VS over the square root of 2 oh, this is just equal to, the whole thing is equal to 133 point, nope. Nope, that's not right. Plugged in bad math. the whole thing is equal to 1.976. And the unit is watts. Okay, so we could have done this, but the issue with doing this is that you would have had to have taken Vs squared, well, Vs RMS squared over ZRMS. Where ZRMS is just Z divided by the square root of 2. You could have done that. That's not wrong. We ended up doing that anyways, just in more steps. Wanted to show you that's true. So, this took one board. I did more math than I probably needed to. Just fine. How do you feel about taking a 10-minute break, coming back here at 9:05, doing another one of these examples? Let's do it.